Welcome to lesson 5 of this A-level physics course by me, Dr. Fox. This one's all about classifying stars now. So we've sort of taken a leap out of looking at telescopes, now actually looking at things that we might actually want to look at. Stars in particular, we touch upon galaxies in the AQA qualification with this, but generally it's stars with using the absolute and the Hipparcos scale, which is this crazy scale that came up a few hundred years ago and is now being stuck. I think the only place it's stuck is in the AQA physics course. Amateur astronomers use it, of course, as a very quick way of being able to describe the differences in brightness between them. But I'll talk you through the craziness that is the Hipparcos scale, and then some of the calculations that you have to do around it. It does feel like a bit like painful. A lot of professional astronomers would not use the Hipparcos scale. They use different scales. But anyway, nevertheless, let's do it anyway. It's good brain exercise. It's like doing crosswords. It's good for you. You're definitely going to feel well exercised. And part through this lesson, you're going to go, what? Really? Do we have to? But yeah, I'm afraid you do. But once you get on top, there's a sick pleasure out of getting something that's really quite hard. And also, we also like doing things other people don't understand as physicists. So this is one of those things that you can show off about. But you got to keep your thinking cap on. It's really quite incredible, the level of weirdness that it gets to. But we'll get there. And we're going to talk a little bit about parsecs and light years. We're going to save that for another lesson. And then this equation right at the bottom here, which is m minus m equals 5 log d over 10, which is one of the very few equations that we have on the formula sheet, which does not involve SI units. That d, that little d there, is in parsecs, which I'll explain, and the m's are in something called the absolute magnitude scale, or apparent magnitude scale, and it's sometimes called the Hipparcos scale. And it has this unit of magnitude, sometimes called mag, but it's magnitude. So there's the little snippet of the specification, just to really reassure you that we are covering everything in the specification, and a little bit more as well, because I don't like to leave some loose ends. So here's your lesson objectives to get into your notes. To be able to define and calculate apparent and absolute magnitude, luminosity, intensity, and brightness. All these things mean things in astronomy. So we have to be able to know what they mean and where the overlap is and where there isn't any overlap at all. And it gets quite tricky. So I think we need to do this in quite a lot of detail. I'll recap in subsequent lessons as well. To also describe the relationship between intensity and apparent magnitude, that's quite hard. It's about measuring light at the Earth, and there's an SI unit way of doing it, and there's a non-SI unit way of doing it. And you can compare the two. There is ways of doing it, and I'll show you how to do that. To be able to apply the absolute, calculate absolute magnitude using this, you can use it to calculate other things, but generally it's calculating absolute magnitude. And we'll get onto what these things mean. But ultimately, we're looking at how bright stars look in the sky and how bright they really are. So how bright they look in the sky is not the same as how bright they really are. And we'll look at the optical effects. So here we go, some definitions for you. So luminosity is now the new word for power. Now that's the total power radiated by a star in watts. So yes, there is another poor physics teacher joke coming up here. What is the unit of luminosity? Yes, it is. There we go. Just leaving a pause there for giggles. And then we come to the Earth now. So we're sitting on the Earth, we point our telescope up and we work out how much power we're receiving at the Earth. Power per unit area, in other words, if we put a square meter on the ground, how much power are we getting into that area there? So from the sun, we're getting about a kilowatt in that area. But obviously for stars a long way off, we're going to get a lot less than that, much lower wattage coming down. But generally, we talk about the power of a star at its source, so the total amount of power radiating from all surfaces of the star. But if we're measuring intensity, we're only measuring a meter square just on the Earth. So obviously that's going to be a lot less. And then we're going to talk about apparent magnitude. Now, apparent magnitude is the scale which is used for brightness as they appear in the sky. So if you look up with your naked eye, some will be brighter, some will be dimmer. There is a number associated with the bright stars and a number associated with the dimmer stars. The absolute magnitude is how bright they actually are. Now, this is what Hipparcos did. Just stay with me on this one. He gave a scale where he sort of fixed the dimmest stars to have a magnitude of 5-ish. It actually turned out to be 6, but let's go with 5. 5. The sort of medium brightness ones were 0, and the very bright ones were sort of -5. I know that's the wrong way around, but nevertheless, that's what he thought. So 5, very dim. 0, kind of, and then -5, really bright. And so he thought, right, what I'm going to do is chop that up into 100 slithers. So that means the difference in brightness between a 0 and a 5 star is 100 times. That means that 1 magnitude, the difference between 1 and 2, 0 and 1, 2 and 3, a difference in 1 magnitude is the 5th root of 100. I'll say that again. 1 magnitude difference, so the difference between -1 and 0, 0 and 1, 1 and 2. So if a star is brightness 1 compared to a brightness 2, the brightness 1 is the 5th root of 100 times brighter than that at 2, because remember 2 is fainter. Now the 5th root of 100 is about 2.5, so it's about 2.5 times, and I much prefer thinking about as 1 magnitude compared to 2 magnitude is 2.51 times brighter. So a 1 star is 2.5 times brighter than a 2 magnitude star. Yeah, I know, it's ridiculous, isn't it? But anyway, I'll say that all again. And that little scale down the bottom here that I've got might give you an idea. You can see here very bright stuff has very large negative numbers, and very faint stuff has very large positive numbers. In the middle here, you've got the things that are sort of we're interested in. So faintest naked eye star, that's why I said about, it's 6, actually 6. But Hipparcos thought 5 was a good number. And then -5 is a little bit brighter, notice minus numbers brighter, than the brightest, one of the brightest stars in the sky. But object in the sky, which is Venus, the morning star or the evening star, depending. And of course, the moon is incredibly bright, and it hovers around here about the -12.5-ish. So these are the apparent brightnesses in the sky. Apparent, so not actually how bright they are, because Vega is a star, right? It's absolutely booming compared to the moon. And of course, Venus and the moon don't give out any of their own light either. So it means that Vega appears to be around 0, which is a kind of average brightness star. If it's very faint, it's a larger number, positive number. If it's brighter, like Sirius, for instance, which is one of the brightest stars, I think the brightest star in the northern hemisphere anyway, then it's there. So it's that. Yes, I know it's ridiculous. I'm very sorry, but that's the way it goes for AQA. So just to recap, big yellow star at the bottom here. Big positive apparent magnitude means it's a faint star. Big negative number, big negative apparent magnitude is a bright star. So have a good look at that. That's what it is. So remember, small positive numbers, big positive numbers gets fainter as that number gets bigger. Negative numbers, quite bright, but actually the bigger the negative number, the brighter the star is. So there you go, get your head around that. If you have to go and sit in a darkened room for a while to get your head around that, that's fine, go and do that. Pause it. And just to put this into context, if it's the summer now, like it is with me, it's June, go out, look in them right up, and you'll see something called summer triangle, which is a triangle of stars that do. So now we look at what the observer sees. So your observer would see 2 stars that would be exactly the same brightness. You'd have one that is nearby, dim one, and a bright one that's far away, but you'd see them looking almost exactly the same. So they would have identical apparent magnitudes, apparent brightness. but you'd have very different absolute. And the word absolute means how actually bright they are. Now, there's two definitions of the absolute. We're going to stick to the parsec version, which is basically line them all up on a line 10 parsecs away and seeing how bright they are. But the word absolute just means how bright it really is. Apparent is how much it apparently appears from Earth, and it's always from Earth in that one. Okay, so there's putting it into things. I quite like this bottom picture here. The top one just says what I said in the last slide, but the bottom one here is quite nice. So if you look at Sirius, around Sirius, Sirius is a very bright star, but only to us. Because if you actually look at the absolute magnitudes of all the stars, if you looked with a pair of binoculars towards the Sirius area, you will see that Sirius is actually quite dim compared to this group of stars down here just next to it. Still doesn't count as major. And therefore you end up with these weird absolute magnitude things. So the size of the circle is how bright it is. So Sirius is no longer just a proxy little star. And these other ones down here are actually significantly brighter in absolute terms. So if you went and sat next to them, this will be a much, much brighter star, despite it barely featuring down here. So it's really good. So and just a reminder there, luminosity is the total power radiated by stars. What is the power? What is the unit of luminosity? Messed up my own chair. Okay, so here we go. It's not sensible, but this is it. Now, what the examiners really try and catch you out on is this idea that it's times brighter. So if I wanted to work out how much brighter, how much more power output is coming from a particular star. So for instance, if an examiner said, how much more powerful is this star compared to Sirius compared to Vega? Get the absolute magnitudes, and the difference between those guys will give you the multiple. So for instance, if you had a star that was 0, like Vega, and if you had a star that was just, let's say Sirius is -1, it's not, but let's just say it's -1. There's a difference in 1 between them. So I could say that Sirius is 2.51 times brighter than Vega. And just like I've said here, the apparent magnitude 5 is this. So it means that the magnitude 5 star is 2.51 times 2.51 times fainter than the magnitude 3 star. So you get that idea, you multiply them. It's 2.5 to the power of however magnitudes it is between them. And that's a very powerful way of doing it. So in other words, if you take any difference on this scale, so for instance, -3 to 6, like a difference of 9 on the scale, 2.51 to the power of 9 tells you how many times brighter or fainter, depending on which way you want to go, on that scale. So a magnitude 6 star would be 9 difference magnitudes to the -3. But it would be 2.5 to the power of 9 times fainter than a -3 star. So it's that idea that one step on here is always a multiple of 2.51. And all I have to do is do that to a power of the differences between them. And I've got the differences between them. So there you go. Fact. Big red box at the top. A star of magnitude 0 is 100 times brighter than magnitude 4. Absolute magnitude is again a bit of a weird one. And this is where again we have to suspend our probably logical mind and think, why is it 10 parsecs? Because it's a nice round number. So they picked 10 parsecs, Hipparcos. I assume Hipparcos did it. And basically they make all the stars line up on a 10 parsec line away from the Earth. So you get the Earth and you say, right, everyone, line up on that line and we'll see who really is brighter than everybody else. So what you do is you get the stars that are a long way off and you bring them close to 10, and you get the ones that are nearer and you push them back to 10, and then the magnitude that they are there is actually how bright they are at 10 parsecs. So this gives you the absolute magnitude. It's a measure of the absolute output. It's not the output of it, because obviously they're still 10 parsecs away, but nevertheless it's a good measure of it. So absolute magnitude is that. So therefore if you have m minus m, little m is apparent magnitude, and big M, which is our equation that I showed you at the start, we'll start to be able to see a comparison between them. So then you can work out how far away they are. So therefore this bottom little diagram here is quite useful. The star is actually that distance away, but if I brought it to 10 parsecs nearer, it would be a bigger number. 0.1, hang on, gotta be careful here. It's a smaller magnitude, but nevertheless it's a brighter star. So the apparent magnitude is 3, bigger number. Absolute magnitude is a smaller number, but that means it's a brighter star because it's closer to the negative end. That's how we do it. The trouble is the word bigger really gets quite tricky here. So real distance here is, well, that's about 25 parsecs or something. But if I brought it close, of course it would seem to be getting brighter. It will be getting brighter, therefore my absolute magnitude value goes down. Okay, so let's look at some data. This is I've nicked this from an AQA paper. We've got Sirius, Pollux, and Castor. Pollux and Castor are the two stars in Gemini. Astrology is Codswallop, by the way. Sirius, of course, there as well. You've got apparent and absolute magnitude. You've got n minus m. Why do they give me n minus n? That's always an interesting one. N minus m is really good because it gives you an idea of how far away it is. Notice that Sirius, minus 1.46, 1.43, it's a minus number. So if that n minus m is negative, it means it's near. It means it's nearer than 10 parsecs away. Of course, this is in light years. I'll come back to light years. It's just 33 light years is about 10 parsecs. It's another measurement of distance. But to give you an idea, the ones that are further away, Castor's much further away, 52, you can see that that is a positive number. N minus m is a positive number. And 0, it's when it's absolutely on 10 parsecs. And you can see 33 light years is 10 parsecs. So this is less than 10 parsecs, this is 10 parsecs, this is greater than 10 parsecs. So therefore your negative n minus m value will give you a good idea that it's close. If it's a positive n minus m value, long way off. So it gives you an idea of immediately whereabouts they are. And of course you can do the calculations to work out actually how they are. Now I'll put here, sketch an idea. This is a good so in other words, put them on a line and you represent the size of the star will tell you how bright it is and what sort of lineup they are, because these numbers are really quite confusing, so it's good to get it. So let's do this in order. So the absolute magnitude 1.43 at 9. So let's put Sirius near the Earth. 1.43, 1.1, 0.59. So this is actually the dimmest of the star. So it's got a higher magnitude, so it's going to be the one that's the dimmest. So do a little small circle close to the Earth. If we now go to Pollux, put it at 10 parsecs and put it a bit further away from the Earth, it's 1.1. It's a little brighter, so make that circle a little bit bigger. And then as you go to Castor, it's the brightest of these three, 0.59. So therefore, put them at 52. So, you know, about, what's that? How many parsecs? One a bit parsecs away. Sorry, 15-ish. My apologies. Okay. Right, and here's the equation. You're given this equation. It's a very weird equation. It's an important example equation, which we use an awful lot in this unit of the A-level AQA physics. So, apparent magnitude, little m, minus absolute magnitude. Top tip here, just watch the minus signs, because you may be minusing a minus, a minus, a minus, a minus in this case. So 2 minuses make a plus, but 2 wrongs do not make a right. 5 log d over 10, distance in parsecs. So distance in parsecs is not an SI unit, in parsecs. It's got to be in parsecs. And there we are in this little blue box here, just the recap from what we did. And of course, we can do some practice. So here's some 4 straightforward questions. I'd like you to use that. If you haven't used logs before, remember, log is just the power to which 10 is raised to make the number. So classic example, 100. If I want the log of 100, it's 2, because that's the power to which 10 is raised. So whatever the log of whatever number is, it's just what power I need to raise 10 to get that number. So log of 1,000 is 3. Why is it 3? Because 10 to the power of 3. 10 cubed is 1,000. 10,000. Do you see where it's going? So what's the log of 10,000? So what power do I raise 10 to get 10,000? Oh, it's 4. There you go. So you end up with log. It's an easy way of being able to represent very large numbers in a very easy scale. And how you unlog something, of course, is that you do 10 to the power of it. So get your calculator out. Old calculators are different, so you have to work out how you unlog something. It's basically 10 to the power of something, whatever it is. Okay, so there's your questions. Have a good look at those. Pause this video now, and I'm going to show you the answers in 3, 2, 1. There you go, in really unhelpful yellow. Hopefully you can see that. So there you go, there's the numbers in there. You sort those out, and then you end up with those values. And the question 4 is very common, which is appear brighter on Earth, so you just have to look at, because 0.95 is brighter than plus 4. That means that so it is star B, which is 0.95, because it's a lower number. Near a negative as well. That's a good way. I always think of it as near a negative. Okay, so this is what we've done so far in all the lessons that we've covered. Good idea is to just pick one of these randomly and sketch out everything you know, and then go back and look at your notes. So for instance, you might pick your birthday. So you might be born on the 5th of May. So 1, 2, 3, 4, 5. Refraction telescope. Go and do draw out the refraction telescope. All the lines, the 3 parallel lines going through. You might be May. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Across apparent magnitude. Define apparent magnitude, and so on. Do about 3 or 4 of these every single time you recount one of those lessons, and then it will get in here. It will get in long-term memory. Okay.